Welcome to Cheenta Statistics and Data Science. Today we are going to solve a problem from CMI Data Science 2022, problem number 13 and 14. Now, let's start with problem number 13. The problem says that we say that a subset S of a finite set U is large if mod S is greater than mod of U minus S. This is basically the difference. So, where this slash S denotes the elements of U which are not in S. And this notation denotes the number of elements in a set T. This mod of T denotes the number of elements in a set T. So let X be the number of large subsets of the set X, which is this, the natural numbers from 1 to 10. And let Y be the number of large subsets of this set capital Y equals to 1 to up to 9. Which of the following is true? So basically it is said that a subset of a set is said to be large if it has more elements than its complement, right? And this capital X is given set, and we have to then this small x denotes the number of large subsets that can be formed from this set, and similarly this small y is nothing but the number of large subsets formed from this set capital Y, and we have to find the values, right? See, for x for the set X, which is nothing but this, a subset S is large is if its cardinality, that means if it's the number of elements in that subset S is greater than equal 6, right? Because if it contains 6 or more elements, then its complement is going to contain 4 or less elements, right? So in that case it will be a large subset, right? So this is large if mod S is greater than equal 6. That means it is either 6 element subset or 7 element or 8 element or 9 element or a 10 element, right? So basically X is nothing but the number of ways we can choose a 6 element subset, which is nothing but 10 choose 6, plus the number of ways we can choose a 7 element subset, which is 10 choose 7, and so on up to 10 choose 10, right? So this is X. But it might be a bit difficult to calculate this because we have to calculate each of these individual things, right? So what we can do is, see we can use a trick. See now, 10 choose 0 plus 10 choose 1 plus 10 choose 2 up to 10 choose 10 is nothing but 2 to the 10, right? Because we know that this is identity, we know that. Now, n choose r is actually n choose n minus r. This is also true, right? So this entire thing can be written as this 10 choose 0 up to 10 choose 4 is nothing but same as 10 choose 6 up to 10 choose 10. Think about it, because 10 choose 4 is equal to 10 choose 6, 10 choose 3 is equals to 10 choose 7, and so on. 10 choose 0 is equals to 10 choose 10. So this entire thing, this particular thing, this part and this part is nothing but the same. Now this part is x, right? Remember, this part is x. Remember, this part is x. So we have this one is x plus 10 choose 5 plus again this one is x. So x plus 10 choose 5 plus x equals to 2 to the 10. Therefore, x is nothing but 2 to the 9 minus half into 10 choose 5. So 10 choose 5 is nothing but this. Now this part is quite easy to handle, right? So this is nothing but 386. So x turns out to be 386. Now the same reasoning follows for y. Similarly, for y, this is the set y, capital Y equals to 1, 2, up to 9. Subsets with mod s greater than equals 5 are large, because here the number of elements in y is 9. So for any subset to be called large, it has to contain 5 or more elements, right? So that means y is nothing but 9 choose 5 plus 9 choose 6 and so on up to 9 choose 9, right? Just the number of ways we can choose a 5 element subset or a 6 element subset and so on up to a 9 element subset, right? Again, just using the same trick, 9 choose 0 plus 9 choose 1 plus 9 choose 2 up to 9 choose 9 is nothing but 2 to the 9, right? Again, this part from 9 choose 0 to 9 choose 4, this one, and 9 choose 5 to 9 choose 9, this part. These two parts are the same, this part, because see, 9 choose 5 and 9 choose 4 is same, 9 choose 3 and 9 choose 6 is same, and so on. 9 choose 0 is 9 choose 9, same. So this entire thing and this entire thing is the same, and this is nothing but y. So y plus y equals to 2 to the 9. So y is nothing but 2 to the 8, right? Which is 256. So basically y turns out to be 256 and x is 386. X is 386 and y. So option B is the right answer to this problem. Very easy problem, right? Maybe the only trick was maybe to shorten the calculation a bit, was this trick to use this identity, right? Other than that, everything was very easy, right? So yeah, there you have it, the solution to this problem. So let's go to the next problem, problem number 14. So 14 says that a ternary tree starts with a single root node at the top of the tree. Each node in the tree can have up to 3 nodes as its children. No node in the tree is the child of two different nodes. A node which has no children is called a leaf node. The children of a node are drawn below it, connected by edges. The level of a node V in the ternary tree is the number of edges in the unique path from the root node to V. Thus, for instance, the root node is at level 0 and each child of the root node is at level 1. Okay. A complete ternary tree is a ternary tree in which each each the first condition, each non-leaf node has exactly 3 children, and number 2, all leaf nodes are at the same level. This latter level is called the height of the complete ternary tree. The complete ternary trees of height 0, 1 and 2 respectively are shown in the following in the figure below, where we use the symbol this to denote a node. So basically this is a ternary tree of height 0, this is of height 1 and this is of height 2. So basically this is the levels. You can see this is of 0 level, this node is at level 0, this the top levels, the top nodes are at level 0. The next nodes are at level 1, these ones, and and under them are of level 2s, right? Level 2. So basically this thing is given. So what is the total number of nodes in a complete ternary tree of height 9? So basically if we were to draw a complete ternary tree of height 9, how many nodes will be there in that complete ternary tree, right? So obviously we can't draw that in the diagram and calculate and count them. It's very difficult. It's going to be extremely large. So see, the number of nodes in a complete ternary tree of height 0 is equals to 1. See, it's given this is of height 0. This tree is complete and its height 0 and the number of nodes is 1. Again, same thing, the number of nodes in a complete ternary tree of height 1 is equals to 1 plus 3. Why? See, this is one node and this again 3 nodes. So in total 4 nodes, right? This is of level, this is of height 1. So a height 1 tree, complete height 1 tree contains 3 plus 1, sorry, 1 plus 3 nodes, which is basically 4 nodes. Similarly, for the height 2 tree, the number of nodes in a height 2 complete ternary tree of height 2 is equals to 1 1 node plus these nodes, that means 3 node, and this again this 9 nodes, right? So 1 plus 3 plus 9, right? 1 plus 3 plus 3 into 3, that means 9. So basically 13 nodes. So in this way we can have a general idea of how to count, right? The main thing is we have to know how to count. We have to see the pattern. See, in a complete ternary tree of height 9, the leaf nodes are of level 9. See why? Because in a tree of height 2, the leaf nodes are of level 2. See this, here the leaf nodes are of level 2 because we are using two edges to get to them. This is the first edge and this is the second edge. Again, this is the first edge and this is the second edge, and so on, right? So in a tree of height 9, the leaf nodes are of level 9, right? So adding the number of nodes cumulatively, basically, let nk, this nk denote the number of nodes at level k. Okay. So n naught is nothing but 1 because n naught counts the number of nodes at the first, at the 0th level. That means that means at the top. In the top there is exactly one node, right? So it's 1, which can be written as 3 to the 0, right? Can be written as that. So n1 is nothing but the number of nodes in the first level, right? In the first level. Now in the first level, since this is a complete ternary tree, that means each node is going to have exactly 3 children, right? So n1 is nothing but 3 into n naught, because the n naught, the first node, topmost node is going to have 3 children. So 3 times n naught, that means 3 to the 1. Again, n2 is nothing but 3 into n1. Why? Because each of those n1 n1 nodes is, all of them is, each one of those n1 nodes is going to have 3 children. So 3 into n1, that means 3 square. So we can actually have a pattern. So n n naught is 3 to the 0, n1 is 3 to the 1, n2 is 3 to the 2. So in general, n9 is 3 to the 9, and n9 counts the number of nodes in the last level. That means the level 9, right? In the level 9. So that means we have actually found out all of the nodes in the individual levels. So we can just do what is What we can do is just add them. So the total number of nodes in a height 9 ternary tree, complete ternary tree, is nothing but adding them 3 to the 0 plus 3 to the 1 plus 3 to the 2 up to 3 to the 9. So this is nothing but a geometric progression. This is 3 to the 10 minus 1 divided by 2. This is the answer, right? We have actually found out the number of nodes in the individual levels, starting from the first level, the zeroth level, the first level, the second level, and so on the ninth level. That's it. And then adding them will get the answer. Very easy. Right. So this problem is actually, it seems, maybe it might seem a bit difficult, looking at the entire problem a bit longer, a bit larger in terms of a size, but it's actually very easy problem. Very easy problem actually. So just you just need to know the pattern of how to count. That's it. So yeah, there you have it. The solution to this problem. So do like, share, and subscribe to the channel for more exciting problems. See you till next time.